Welcome back, everybody. The topic today and also next week is to try to finalize first the part which deals with decision trees. And then we are going to look at what's normally called support vector machines. I see that sometimes the translation here can be pretty funny on the live text, but it's decent. So if you were to speak in Norwegian, actually, it would give you quite some funny, because then it would desperately try to translate what you're saying in Norwegian into English. That's pretty fun. But hopefully it recognizes the way I speak, although we do have an accent, so I can't escape that. Now, anyway, one of the things I wanted to remind you of is the fact that we pushed the deadline for project number 2 to next Wednesday. And one of the reasons we did that is that we did push the deadline for the first project with 5 extra days. So in order to have roughly a month between each project, we decided just to push it a little bit to a date later, which is now Wednesday next week. So hopefully that can help you in wrapping up the discussions and everything. Now, I also wanted to mention one thing with decision trees and sample methods like those we started to discuss last time, is that we've had people who have studied these methods as part of project number 3. So one of the things which we want people to deal with in project number 3 is to use at least 2 to 3 methods which we have been teaching during the semester, and then analyze either your data set. We are going to propose some paths, and there is one path which many people have liked to deal with, and that's the discussion of the solution of diffusion of differential equations, because many people will deal with that in their thesis topics. So to see different types of methods is something which is of interest. And many people are taking in parallel a course on partial differential equations, so that matches pretty well this final project. But then you should feel free also to propose projects. And I'm going to send you an email, because next week, what I would like to suggest is that we try to use Friday as a day where people can present alternatives to project number 3. So we've used to have a kind of, not exactly a full workshop, but a kind of mini workshop where people actually present data sets or topics they would like to explore in project number 3. And what often happens is that some people in the audience think, oh, that was interesting, I would like to join that group, if possible. And then you can have more people collaborating on the same project, if that is of interest. So I'm going to send an email, and what people typically do then is that you make a short presentation, 5 to 10 minutes at most. These are the data sets I'm interested in. This is a topic I would like to explore. And then we can have a discussion with everyone. That has been very fruitful. So some years we have the full 2 hours of a Friday next week or Thursday, depends on the day. And other times we just have just one lecture. So you will receive an email about this by the end of this week, beginning of the weekend. And just to keep in mind, like this problem with or this topic with the decision trees and ensemble methods is something which can define its own project. And there was a group last year which actually did this, and they developed their own codes for ADABoosting, for gradient boosting, and then compare that with, let's say, neural networks and other methods for class. Essentially what they did was to look at classification problems. But the interest then was actually to look at these different methods. Okay, so what we did last week was to discuss the basics of decision trees. And we looked at a very popular algorithm, which is called the classification and regression trees, or CART. And that can be used for both classification and regression. And we saw how we could grow a tree. We could split the branches. So the most common way of dealing this is to have a binary splitting. Yes, no, true, false. And in classification problems, this is normally done by calculating either the entropy, where you know that if the entropy is a quantity which is defined so that if it is 0, that means that you have a pure state. There is no mixing with anything else. The bigger the entropy, the more unlikely the result is, or the probability, and that means that you have a high degree of mixing. So the entropy is one of the quantities which is used to split the branches, and the other factor which is used is the so-called Gini factor. You have other measures, but the Gini factor and the entropy are the most used ones to make the splitting. And as I said, these two factors, the entropy and the Gini factor, they contain information about whether the state or the system is pure. So if you have a node which has only one type of outputs, then the entropy and the Gini factor are equal to 0. And we call that a pure node. And then clearly your tree terminates, or the building of the tree terminates, and you just have what we call the leaf node. Then, since a decision tree normally can lead to overfitting, because you can trim it down to really reproduce every single data point. And then you clearly end up in a situation where you have overfitting, which we don't want to deal with. And the solution to that is actually to aggregate trees in different ways. And one of the standard methods is this bagging, which means simply boosting with aggregation. And in that case, you grow trees which are lookalikes, whereas with random forests, you have the possibility to grow trees which have different root nodes. And in that way, you develop a more heterogeneous set of trees, and you can actually show that the correlation between the data then, or between the different trees, is much, much smaller than if you have a homogeneous tree. Then, what we started scratching the surface of is boosting methods. And boosting methods, you can think of them, if you're looking at linear regression, you can think of them as methods which are pretty similar to linear regression. So you're taking a function, you're producing an output with that function, and you keep improving upon a simple function till you more or less reproduce the data you are meant to reproduce. So linear regression starts by, or other boosting methods, they start with a weak learner, and then by successive iterations, you try to improve upon that so that at the end, you have a model which reproduces the data to the degree of accuracy you want. And the typical way of doing this is to penalize the results which are wrongly reproduced. And you will see that in one of the more popular algorithms for boosting, which is called adaptive boosting, or ADABoost. And that's one of the algorithms we're going to discuss today. This algorithm is actually something which is easy to implement, and you will see that. So if this is a path in project number 3, I mean, it's not that difficult when you see the algorithm to write a program yourself. And in that program, you could simply use a standard decision tree, which is programmed in a highly efficient way in scikit-learn, and just use that one as an entry point. So you can think of what we're doing now as a kind of modified linear regression. So let me, before we move on, let me quickly say something about the final topics for this week. So if we end up a little bit earlier tomorrow, we're going to start with the last topic, or actually the second last topic, but the last supervised learning topic, and that's support vector machines. So support vector machines is a method which essentially leads to a convex optimization problem. So instead of you taking the gradient, you're actually going to optimize a Lagrangian, if you're familiar with that from courses in mathematics. So it's a slightly different optimization problem. And it was a very popular method, but all these methods which we have been looking at till now, they suffer from the fact that you deal with linear algebra methods, which means again that you have to be able to store large matrices. And clearly when you go beyond the capability of how you can store larger and larger matrices, then clearly you would have to rethink the type of methods you implement. Then the really, really last topic, which we're going to look at the end of the semester, which is the last week, is about the principal component analysis and unsupervised methods like clustering. But there we're just going to scratch the surface. before we end the semester, which will be on November the 25th, which is the last lecture before the exam period kicks in. Okay, so there are some videos which are actually I think they're pretty good. And you can take a look at them. And else of the textbooks which we have recommended, the one by Hasty et al., in particular chapter 10, is the one which covers many of the mathematical details. And then we also have the textbook by Geron, which is more a applied textbook where you can see many programs which illustrate these methods. So I'm going to switch back to our notebook and just remind you a little bit about what we had last week. And now I just have to find it back again. So I quickly wanted to remind you of how we included things and how we run things last week. So in this case, I'm using the same data set which I've actually been using in project number 2, and that's the Wisconsin breast cancer data. And you've probably seen this ad nauseam now, but I'm rerunning everything with decision tree classifiers, a random forest classifier. There is an implementation of support vector machines for classification, that's SVC, which we are going to discuss in more detail next week. And then we have logistic regression, just to give you a feel of what the different methods actually give us. And here we scale the data and perform simply a calculation of the different, with the different methods and look at their predictions. So we have a random forest classifier with 500 trees. We use the entropy to make the splitting. We have a decision tree as well, and then we have logistic regression, as you can see here. And in the case of the decision tree classifier, we don't put a limit on the depth of the model here. But you will see now when you run this with the different test data and so on, you will see now that decision trees is normally the method which performs the worst. Logistic regression, and this is something which many have seen in project 2, does surprisingly well on this data set. So surprisingly well that many people are disappointed about neural networks. So this goes a little bit back again to what you would typically end up doing when you do machine learning. You would test several methods, and people tend to pick the one which gives the best result, but you have to argue and have to understand why this method is seemingly the one which does the best job on that data set. But this would be a typical example of what you would see in publications and in research. And in this case here, I plotted the confusion matrix, just to quickly remind you of that. It's a very useful way of plotting it. And this is the result with random forests. And the random forest in this case gives a 98% hit for this data on both the true positive and true negative. And later we are going to see that gradient boosting is going to elevate this prediction to 100% correctness. So gradient boosting is actually one of the favorite methods. And you will see that there is a popular library which is called XGBoost, which stands for Extreme Gradient Boosting. And we are going to go through the details of gradient boosting. So you can actually, if you want to, you can write your own code. And that is a method which actually wins a lot of competitions on, in particular on classification. So it's widely popular, and in most cases on classification, it actually outperforms many of the deep learning methods. And here we plot again these different curves. But what I want to do now is first to quickly remind you a little bit of what we did at the end of last week, and then we are going into the details of a classification problem. So the first thing we did last week was actually to give a kind of bird's view on boosting. So the idea is to combine a weak classifier in order to create a good classifier. So this was close to what we did when it came to this voting model, where you can actually just repeat and repeat an experiment, like tossing a coin. And you know that if you just toss it 10 times, you may have 6 tails and 4 heads. So you won't get a 50-50 distribution. But if you do this again and again and again, and say you do it 10,000 times, then there's a close to 97% likelihood that you will get the right prediction, 50-50. So what you do here is actually to start with a weak, cheap method. It can be something which is barely above a random selection. That means 50-50 if you have two cases. So the idea is that this weak learner is something which is easy to use. And then by repeated operations, so what you would typically do, and the example which we looked at last time was actually the usage of a linear function, b, and then we showed how we can repeatedly improve the parameters. So there are parameter beta m, and there's a parameter gamma m. You are free to put these parameters in other parts of the function you want to optimize. So the function you're going to optimize is this function f by using a weak learner, which is this function b. So that could be a decision tree which is shallow. It could just have a depth of 2. And in the examples which you will see below here, you can play around with the depth of the trees and see how that changes the output. So the whole point is that you want something which is quick and fast, and it's easy to evaluate. And just to remind you, when you've been doing neural networks, every time you go through a given hidden layer, you're actually producing an output which hopefully gets better and better. So this function here, which you've been applying in the hidden layers, for instance, is something which every time you backpropagate and then you start a new forward propagation, then the output is supposed to be improved over and over the different iterations. And at the end, when you reach the last final layer, you have an output which should mimic what you want to reproduce, so be as close as possible. So the example which we looked at last time was actually a function where we now have a dependence on the output values y and f. So this is our standard mean squared error, unsurprisingly. And what we did when we did linear regression is that we simply had a design matrix times beta, and we found the optimal value of beta, as you've seen zillions of times now. So what you would do then in this method here is that you would establish a cost function, and this cost function is now defined by your model, so this m, and this m is now generated in an iterative way where you would start with an initial guess. This could even be 0 or some other guess, which you will see a little bit below how you can initialize it in other ways. And then you would loop from m equal 1 to uppercase m. You would minimize this function in this particular case with respect to this parameter gamma and beta. You would find the optimal parameters for that specific iteration, and then you would update the new values of the function. And then you do this m times, where m is the upper case m, and when you've done this m times, you have an estimate from your model, which hopefully is as close as possible to the values you want to reproduce. So in a certain sense, it looks like standard linear regression, except that now the parameters, beta and gamma here, they are actually inside the function here. So in a certain sense, it's no longer linear regression because you don't have a linear dependence on the parameters. And one of the examples we looked at last time was simply to assume that this function b was just a polynomial of first order x with an unknown parameter gamma. And then what we did then was simply to optimize. So you start with the first optimization. This is the function you optimize. And that means you need to calculate these two gradients. One with respect to gamma and one with respect to beta. And you will see a little bit later that when you call, let's say an ADA regressor, adaptive regressor, or ADABoost regressor, or ADABoost classifier, you will have to fix the learning rate because you're calculating gradients, either with gradient descent or stochastic gradient descent. So this is something you can specify. And I think the default in scikit-learn is a stochastic gradient descent. But you need to specify a learning rate. So everything which we have been discussing before with the gradient descent methods and so on, this comes in here in full scale. So if you want to write a code for this, you could then reuse your gradient descent code from project number 2. So I hope you can see the basic steps here. And when you've done that, in this particular case, you can actually reorganize it, but you need actually to solve it numerically. And you get a set of equations which then can be solved numerically, or you would simply just run this through either automatic differentiation or your own gradient descent without automatic differentiation. And when you've done this, you find the next values, and then you have a function f1 of x, which is now beta 1, plus the multiply with this term here. And then you repeat this m times. So this is an example of an adaptive classifier adaptive regressor with a weak learner. The weak learner here is a first order polynomial. But you could have replaced that weak learner with a decision tree. And that's normally what is done when you look at the boosting methods, that normally you don't have like a polynomial here, but you would have a decision tree, which is pretty shallow as a weak learner. And then you would keep iterating on this. So in a certain sense, that means that you are aggregating many trees, but trees with different properties. So if you look at what you're doing here, what you're doing now is a kind of a regression in a certain sense, in which the features of each sample x of I, they are the outputs of some weak learner applied to this x of I. This is basically what we've been doing here. Now, there's one small digression which I wanted to bring up before we move on to the classification piece. And that has to do with different types of cost functions. So we've been basically looking at the root mean squared error, or the mean squared error. But there are actually modifications, because the mean squared error is a function which normally penalizes the outliers. But you can actually dampen that in case you have lots of outliers. There's a possibility to actually combine different types of functions. So you could have the mean squared error for some range of values, and then you could have an absolute value for the other types of values. This leads to a cost function, which is also widely used, which is called the Huber cost function. So let me just show you what it looks like. And let's just switch back to the whiteboard. And then we are going to look at the boosting for classification and the basic recipe which is needed in order to do that. So let me just bring that up. Yeah. So in general, what we have is, when we have been doing regression, we have essentially just met the mean squared error. So let's just write this down here. So in the regression cases have mainly utilized the mean squared error. When I say regression cases, these are the regression cases we have looked at during the semesters, the mean squared error. And that means that we have a cost function which runs like 1 over n, and then we have an I from 0 to n minus 1, and then we have a y of I minus the y of I tilde squared. Now, the problem here is that if you have many outliers, this can clearly lead to problems in the fitting of a specific model. And as you saw in project number 1, this is particularly important when you have few data. So if you have tons of data, many of these outliers, they get washed out because normally you don't have that many. But in many cases, if you have 100 data points, you can often risk that you have lots of noise, and then clearly outliers can play an important role. And even if you go to a high degree of a polynomial fitting or any other type of functions, what you would see is that the fit will perhaps not be the best possible one. So when you have outliers, or lots of outliers, what is pretty common to do then is actually to define a new type of cost functions. So with many outliers, you get penalized when you are trying to train a model with the mean squared error. So you can easily run into cases into a poor mean squared error. So what is done then often is to define a new function, and this function is normally called the Huber function, and that combines the mean squared error with the absolute error. So this is normally called the Huber cost function, or just the Huber function, or the Huber loss function. So that combines, and now I'm just writing the mean squared error like this, y minus y tilde. So it's the norm 2 squared and the norm 1 of y minus y tilde. So this is just the absolute value. So that means that you will not be able to obtain a nice analytical result, but you would have to calculate the gradients numerically. And you would have an if test in case your value y is smaller than a certain value. And typically then, what you would have is something like this. So you would then define a cost function which depends on this y, and let's write it like a y tilde, and it would look something like this. You could have now y minus y tilde squared if, and I'm going to squeeze that in here, if the absolute value of y minus y tilde is smaller than a certain quantity delta. So this is something you have to decide. That means that you should actually look at your data if you have the possibility. And then you will see this next term in different disguises, but the most common one is actually to see this in terms of a variable delta, which you have to decide upon. So this is a parameter which you decide, multiplied with the absolute value minus delta squared divided by 2. And you will do that in the other cases. So if you want to make a plot, so this is just one of many functions. Now, you're also going to see when we do the classification case with boosting, which leads to ADABoost, there are many ways in which you can define the way you quantify the error in your model. So there are no essentially unique ways of doing that. And this depends a little bit on what is numerically efficient and what is relevant for the data set which you have. So if you have if you look at this function here, it would look, if you make a plot of it, so let's just make a plot here. And you would have 0 here, 1, 2, 3. I can still count, at least to 4. So if you take the mean squared error, so this is pretty schematic. So you would have the mean squared error would be something like this, quadratic behavior. But then what you would do then is that this Huber function, or the absolute value, kicks in at a given value here. So you would have something like this. So this would be the Huber function which kicks in. So this is the absolute value. It means now that your cost function would actually be given by this function here. It has the mean squared error here, and then it follows this function up here. So this is a function which normally tends to dampen so-called outliers. So you're assuming now that in a small region you don't have any outliers, whereas you may have lots of outliers in another region. So this is a typical function which many people actually end up using. This was a small digression. So what I want to do now is actually to move over to boosting and classification. So let's call this boosting for classification. And the algorithm which we are going to look at is an algorithm which is widely popular, and it was actually introduced 20 years ago, and it's called ADABoost. So this is the one we're going to describe now. So we have, as usual, we have a data set. So our data set is given by this domain, D. This is given by D here, and we have x0, the output, and then inputs x1, output y1, and so on, up all the way up to xn minus 1, or yn minus 1, like that. So each x of I has an associated class. So what we are doing now, each x of I has a class, an associated class. Because now we are looking at a classification problem. And in the algorithm which I'm deriving now, this is going to be defined in terms of a binary problem, where I have -1 and +1 as the outputs. And you will see quickly why we are going to deal with -1 and +1. There is nothing which hinders you to redefine it to 0 and 1, or if you have 0 and 1, to redefine that to -1 and +1. Now the tricky thing now is actually how do we estimate the error we are doing by iteration from iteration. So if we now want to repeat what we did in the regression case, we are now going to build up a weak learner. And the weak learner is going to be a decision tree, but a decision tree for classification. So we are going to define a set of weak learners, of classifiers, or what we might call weak classifiers. So these are our learners, our weak learner. And each one of these is now defined by a given function. And I'm going to call this function here, as we did before, I'm going to call it for B. There's going to be a B1, a B2, and all the way up to a B of M. So we are going to perform this iteration again M times, except that now it's a decision tree for classification instead of a decision tree for regression. And then each one of these and each of these outputs a B of J for one of these with an input x of I, which is now either -1 or +1. So either true, false, or -1, +1. Okay, any questions so far? So I'm just defining the way we are going to perform the iteration here. That means that after m-1 iterations, we are going to have a new function. We have a function then, an f, as before, m-1 of x of I, which is now simply given by some parameter, alpha 1, multiplied with b1 of xi. So we're just adding up all these guys, plus alpha 2, which is a parameter we have to determine, b2 of xi, and this goes all the way up to an alpha of m-1 of bn-1 of x of I. And this is then used to define the function, so which we use in the next iteration. And we use that one in the next iteration to define a new function f of m of x of I, which is going to be equal to f of m-1 of x of I, plus the new parameters to determine am, alpha m, multiplied with bn of x of I. And this is something we continue till we reach the last iteration, and that will be the quantity which we feed back as our prediction. Okay? And now the question is, how do we find these parameters alpha? That's a big issue, right? We have decided that B is going to be a weak learner. So that will be a decision tree. Let's say with a depth of 2 or depth of 3. It's up to us to define how deep the tree should be. And if you go into textbooks and articles, you will typically see that people tend to define the tree to have a depth between 4 and 8. If you go to deeper and deeper trees, that means that you will get better and better precisions, but then you are in a way defying the whole scope of these boosting methods. So how do we find the alphas? These alpha of I. Now let's now define an error, because we are going to compute an error, and that's the quantity which we want to drive to 0. So this will also be our cost function. So we define an error. This is also a reason why the cost function is also called the error function. So we define an error, and you will see now why we can use this function. And I'm going to call this an epsilon r. This is the error, which is just a sum over the data which we have of n minus 1. And this is given by e to the minus y of I. And then I have my function of f of m. So this is actually my error at the stage n. So we should actually put an m in here. So we know that y of I takes only 2 values. We have defined that to only take 2 values, minus 1 and plus 1. And this function which we have now, f of n of x of I, gives also only 2 values. So that outputs minus 1 and plus 1. Okay? So the whole point now is that we are going, when we are setting up this error function, you see now that if you have a correct prediction, the argument to the exponential is plus 1. So you have e to the minus 1. So that's a small number. And we are going to multiply that with a weight. And you will see quickly now how this weight is. So this weight is going to emphasize the wrongly predicted results. So if you now look at the argument to this exponential, we know that if a correct prediction what we have then is that y of I multiplied with this fn of x of I is equal to plus 1. So that means that we have e to the minus 1. Then, if wrong, we get a positive argument. Then what we have is that y of I of fn of x of I is equal to minus 1. And then we get a positive argument because we have e to the minus times that function. And that means that this is a value which will, depending on the weight we multiply it with, it can be used to emphasize the points which we describe wrongly. And that means that when we do the next iteration, we can put more emphasis on the wrongly described results and less on the correctly described ones. So what is common to do now, so let's try to set up some of the basic equations now. So if we look at this error, we can now rewrite it in terms of the functions which we have defined. So we have the error at a given iteration n is now given by the sum over all the data points we have. So this is actually summing all the points we have. And then we have an e to the minus, and we have y of I. And then we have the previous value, fn minus 1 of x of I. So I'm simply writing out the function here. And then I have multiply with e of minus y of I. I have this parameter alpha n multiplied with this b of n of x of I. Okay? So I'm going to define now, just for the easiness, I'm going to define a parameter wi for the first iteration, which is just equal to 1. Later, we are just going to put this one equal to 1 divided by n, so that every parameter has the same weight in the beginning. What we can do then is, when we do this, is that for these iterations n larger than 1 then, what we have is that we can rewrite everything in terms of this function. So we have a sum from I equals 0 up to n minus 1. And what I'm going to use now is to define this wi of n. I'm simply going to take the first term here, this term which you see here. And that means that what I have is e to the minus y of I multiplied with the previous result. And we know again that the argument is either plus or minus 1. So we can rewrite this as a wi of n multiplied with e of minus y of I, of this alpha of m, the new values of b of n, and then x of I here. So this weight now is going to include the weight which will give a positive argument to the exponential in case we misclassify, and then it's going to have a negative argument in case we classify correctly. So that means that this function which we see here is going to put more weight on the results which we misclassify. And that's actually the whole idea behind this algorithm, because if it's correctly classified, we know that we have a plus 1, and if it's wrongly, we have a minus 1. So we can rewrite this in terms of the following. So we can have of a function, because now we know that this alpha n times b of n of x of I multiplied y of I is equal to either plus or minus 1. So plus 1 if we classify correctly, minus 1 if we classify wrongly. So we can rewrite this function. We have the sum of I, and now I'm going to be a little bit sloppy here, so I don't write I equals 0 to n minus 1, but we have a sum of I where we now include only y of I equal to bn of x of I, and we've made an assumption that these parameters alpha, m are larger than 0. So it's only the function b which is now our decision tree, which now returns either minus 1 or plus 1. Okay? So what you get then is the same parameter, wim, but then we have e to the minus alpha n, and then we have plus, and then we have a sum of I, but now y of I is different from b of n of x of I, and that means I have my weights multiplied with e, and then I have plus alpha m here. You can always rewrite this in terms of a sum which runs over I equals 0 to n minus 1, and you have a y of I, so I'm just adding e to the minus alpha n and subtracting e to the minus alpha n, and this would contain a new term where we have a sum, but where y of I is by definition equal to bn of x of I. And then we have the wi of n, and this last term is multiplied with e of alpha m minus e of minus alpha m. So I just rewrote these two equations here. Now, since the only part of the right-hand side of this equation, which depends on b of m, is actually this term here. So this is the only part which depends on the value of b of m. The other one does not. That means that when we are going to minimize the error, we are going to optimize this weight factor alpha of n. So what we're going to do after the break now is to take the derivative of this function with respect to alpha m. And when we take the derivative of that function with respect to alpha m, we are going to find the optimal value for alpha m at every iteration. And then we're going to have a recipe by which we can now set up an iterative scheme where in every iteration, by minimizing the error, this is actually what we want. We want to drive the error to 0. Then we are going to find a recipe for the weights and for this parameter alpha n. And then with that recipe, with a closed form equations, we are going to set up the final algorithm for ADABoost. And then we're going to see how we can implement it and what is its performance compared with random forest, for instance. But now I see that we are getting close to the hour, so it should fit to take a small break. And let me just put the recording on pause here. So what we're going to do now is actually to take a closer look at the derivation of these parameters alpha m and how we can actually set them up. So I think the headset should be connected. So for those of you online, can you hear me well? I have a feeling that it didn't connect immediately. So let me just fix this small thing here. And just okay, so it seems that people can hear me well. Let me just reconnect the headset, because they suddenly disconnected here. So they should now be connected. So we should have that. Just test the sound. Okay, everything is fine. So I can keep moving here. My brain is connected to my legs. So if I don't move, my brain doesn't function. Okay. And when you teach this way with Zoom and you stay away from your laptop, I mean, the microphone is pretty weak, so the people online won't hear me if I don't have this, this small headset here. Okay, so what we did before the break was actually to set up the equations for this error. And what we're going to do now is simply to calculate the derivatives of the error with respect to these parameters alpha m, and that's going to give us the expression for the parameters alpha m. So if we do that, it's pretty easy when we do the algebra here, that we get a minus, and then we have a sum over I, and we have y of I equal to, sorry, this is equal to bm x of I, lots of indices to keep track of here. I have a w, the weight of m, and then I have e of minus alpha m. So I just get a minus because I take the derivative of e to the minus alpha m. So I hope you don't get offended if I spell out all the details here. I have a y of I, the sum here of I, of y of I different for bm x of I. And then I have w I for iteration m multiplied with alpha m, and we want that to be 0. So keep in mind that this parameter alpha m does not depend on the index I. So alpha m would now be the same for all the data points which we have. So alpha m does not depend, this is an important assumption, and that means that we can put it outside the summation on I, which is the summation variable. So we can actually rewrite this in terms of an e to the, when we shuffle over to the left-hand side, one of the terms, I have an alpha m, and then I have this summation of y of I equal to bm, so we are classifying correctly. And then I have the weights, wi of m, and this is simply equal to e of alpha m, and then you have a sum of y of I different from bm of x of I of wi of m. And then we can reorganize the equations, and one of the things which is pretty common to do now is actually to take the log of the left-hand side and the right-hand side. So we take the log of the two terms. So when we do that, what we get, if we do the log, we obviously have a minus alpha n, and then we have log, and then we would have the sum over yi equal to bm, correctly classified, of wi of m. And then we have this is equal to an alpha m plus log, and then I have the sum over y of I different from bm. So these are all the misclassified guys, y of m. And then I can reorganize this one. I can just put alpha m on one side. And if we reorganize this one, we can actually find that alpha m is actually equal to a half of log. And then what I have here is a sum over y of I equal to bm of x of I. And this gives us wi of m. And this is divided by the sum where I misclassify of wi of m. And what is common now is actually to define this in terms of the error rate. So you can, if you look at this sum which you have in the denominator and the numerator, you can now define something which is called the error rate. So this is the number of misclassified divided by the number of data we classify correctly. So it's common to actually introduce a parameter epsilon m, which is simply given by the sum over the misclassified ones of wi of m, and divided by simply the sum over all the weights. So I would have I from 0 to up to n minus 1, and then I have an wi of m. So in the first iteration, we are going to give a weight which is equal to all observations. And that's simply given then by what we might call a uniform distribution, 1 over n. So if you look at that, you can then rewrite alpha of m. So take a closer look, so I can actually rewrite this alpha of m with this error rate. So I have two summations. So the first summation is actually something which I can rewrite. If you look at this one, I can then rewrite this one as the sum over 1 minus the misclassified, right? And then if I then divide by the total number of the classification points, so this obviously sums up to 1 if this weight is 1 over n. So what I have here is just a sum which sums up to the weights, to the total weights. And this is then equal to a half of log 1 minus epsilon m divided by epsilon m. Another thing is that when I have defined log 0 to be equal to 0 actually, what you would times 0 if I do that. But we have to be a bit careful, but if the error here is 0, I have 1 minus 0 and then divided by 0. So that actually is something which diverges. I could then say that when this quantity diverges, then my alpha m should just be put equal to 0. So this goes back to the question before the break, that if you now look at this quantity here, if you classify everything correctly, then this term here is actually equal to 0. So that would be a typical if test you would have if epsilon m is equal to 0, stop. So that goes back to the question which we had before the break here. So when you want to set up the algorithm, this is pretty straightforward, but there's one problem with ADABoost if you look at it. The thing with ADABoost which can be problematic is the fact that when we misclassify, we have a positive argument in the exponential function. And this is multiplied by some weights. And that means that we can give an excessive weight on the misclassifications. And sometimes this misclassification part can actually grow in an undesired way. So this is something which can be a drawback with this specific method. But let's look at the algorithm. So the basic algorithm for ADABoost, if you want to write your own code, and as I mentioned before the break, several people have actually done that in this course and implemented various types of decision trees, from plain decision trees to gradient boosting. And this is actually a very useful exercise because it allows you to play around with, for instance, the bias variance trade-off in a very interesting way with decision trees, from decision trees to gradient boosting. And you will see how correlations are better built in when you include different boosting methods, and how you then can actually reduce the variance and the bias of the models. So as we mentioned, a typical decision tree is something which leads often to a case of overfitting, where you can easily end up with a huge variance. Okay, so let's look at the algorithm. So the first thing you do now, if you want to write a code here, you define the domain of events. So if you look at the Wisconsin cancer data, you know exactly how to define that. So you could actually take that data case, and many people have done that in the final project. And this would just go up to the final point, xn or yn minus 1. Then you initialize the weights. And when you initialize the weights here, you would often just set them up in the following way. V0 for the 0th iteration, 0, equal to 1 over n, and that's equal to W1 of the 0th iteration, and that's equal all the way up to the final value of Wn minus 1 for the 0th iteration. So that's a pretty common choice, to actually put the weights the same for all the data points you have. And that enters the calculation of this error. Then you need to define an error function. So that defines your cost function as well. And in our case, we define this as a y multiplied by this function f of m. And I'm leaving out the subscripts. Then you need to define a weak learner. And this weak learner is this function b, which we called. And this is a function which in our case takes an argument x, and it gives output, which is in this particular case, in the algorithm which we wrote, is tailored to the case where the output is minus 1 or plus 1. So the way we put up the weights follows the fact that we chose minus 1 to plus 1. You can choose other domains that will just change the mathematical expression for these parameters alpha, and also for the weights. And you can have more classes, so that's also fully possible. But in this case here, just to illustrate the model, we picked a case which is a binary case, where the output is minus 1 and plus 1. Always be suspicious when people say it's straightforward to implement another method. I did that error once. I gave an exercise and it took me a whole weekend to solve it. It said it's straightforward to see the solution. It took me a weekend. Okay. Then what we would do now, when we have defined the weak learner, so the weak learner in our case is typically a decision tree, a shallow one. So these are normally called tree-based boosting methods. You are not limited to a decision tree. You could actually take a neural network with few hidden layers, for instance. That's also possible. But the decision tree is the one which is widely used in these boosting methods because it's so fast and easy to compute. So this is one of the basic philosophies here. We want something which barely actually does a job beyond 50-50. Then we would now have a loop for m equal 1 to uppercase m. So we will then find the weak learner that optimizes the error. So we want to calculate this the epsilon r by, and in this case, we actually want to optimize this problem here. So we would have a sum over j equals 0, and then we have to have n minus 1, and then we have our wj as a function of m. And this is for the case where y of xi is different from bm of xi. So we try now first to calculate this quantity here, and we optimize that one. So we minimize the error. So that's the first optimization part. So here we optimize. And we call a weak error. Then, when we're done with that, we compute an alpha of m, which is simply given by this quantity epsilon of m. Then the next thing we do is actually to update the weights. So what we're doing here, we find, in this here, we find the optimal b of m. Here we update the weights. So when we have this parameter alpha m, which is assumed to be larger than 0, we update the weights, and then we have wi of m plus 1 is now going to be equal to wi of the previous iteration, and this is multiplied with e to the minus y of I alpha m, and multiplied with bm of x of I. So we have then to calculate all the weights, and then we would have to renormalize, or we normalize the weights. Then we normalize weights, because that enters, if you now look at the equation which we had up here, we did normalize the weights because we are we're defining this quantity epsilon m, the error rate. And in this particular case now, we actually need the normalization of the weights here. So we're just summing up over all the weights, because we need that one to calculate the parameter epsilon of m. So then we normalize the weights, and we have the new. So we will actually have a sum over I equals 0 to n minus 1 of wi of m plus 1. And this is end. And this returns the function which we have labeled f of m of x, which is equal to this function f of m minus 1 of x plus this alpha of m of b of m of x. So that's the final function which we would return, and that's the one which we are now using in order to make predictions. So this is basically the ADAGrad, no, not the ADAGrad, but the ADABoosting method. Now, what you can do now is also to define other types of so-called error functions. And one of the functions which is often used is something which looks like the logistic distribution. And that's normally called logit boosting. That gives us slightly more complicated equations to evaluate, but you will encounter many, many different types of ways to define this error function. Another one is called ADA-real, and there's a subset of such types of equations. So I hope that you can see how you would implement the algorithm. It's actually not that difficult, but I just wanted to show you now some demonstrations when we run with a scikit-learn and see what kind of results we can expect with that. So let's go back to the Jupyter Notebook and take a quick look at what we could expect when we do an ADABoost. So in this case, there's actually a function which is baked in if you don't want to write your own. It's called the ADABoost classifier. And in this specific case, what you now include is your weak learner, which you see here. This is the decision tree classifier. And with the decision tree classifier, you simply define the depth of it. You define how many times you want to estimate the trees. So you want to do a 200 iterations here. you have to decide the learning rate because you're calculating derivatives of the error function. So there is a gradient method which kicks in here, and the same way as we did it in the case with the ADA regression. And in this case, I just opted for a learning rate of 0.01. And then if you use scikit-learn's functionality, you simply make the fit. In this case, I just use the train data here, and then the prediction on the test data. And then you can plot the confusion matrix, you can plot the ROC curve or the cumulative gain curve. If you now look at this set of parameters here, you see now that my ADABoost is actually doing better than my random forest code, because my random forest implementation on the same data set, these are the Wisconsin breast cancer data set, which you're looking at in project number 2. This one gives on the true positive, a 98% score, and on the true negative, a 99% score. So this data set which we have is a data set which is pretty well balanced in terms of true positive and true negative. And then it makes sense to fit the data on true positive and true negative. If you have a very skewed data set where you have few true negative and most of the data true positive, then you could think of another type of score, another measure in order to make the fit. But typically, if you have a kind of close to 50-50 case, the normal situation then is that we would plot a confusion matrix like this one, where we just calculate the true positive and the true negative. And I always don't remember whether true positive means a benign or malignant cancer. I always have to look up the data again. And then I look it up, and then 10 minutes later, I've forgotten it. So I never remember which is which. I don't know why. I can't explain that. So this would be a typical example of how we could run it. We could just now, for the fun of it, we could make the learning rate larger and just see what happens. And we can make the tree deeper. So in that case, you see now it doesn't look that good. So that becomes a parameter we would have to tweak. If we go back to 0.01, which seems to be a better value, which is often a better value in most of the applications, and probably you have noticed that in project number 2, that the learning rate of roughly 10 to the minus 2 to 10 to the minus 3 is the one which normally does the job. Then I could make the tree a little bit more shallow. No, sorry, deeper. And let's see if that changes the results. These are pretty fast, actually. And in this case, actually, it wasn't the result. So this is, again, something you would have to play around with. The depth of the tree, the learning rate, and so on. So it's not that you would get a perfect result in one shot. So these are extremely popular methods, but the methods which are really those which people prefer nowadays are so-called gradient boosting methods. So here in the adaptive boosting or ADA boosting, we actually, in an iterative way, we are improving the quality of the function. But now we can try to improve the quality of the function by looking at the gradients of the functions which we are fitting. And let's see how that can be used. So that's the next type of methods, and that's also a method which is not that difficult to implement yourself. So I want to spell out the algorithms for those methods which I think are easy to implement. So let me see if I can convince you that they aren't that difficult. So if we look at these boosting methods, so the gradient boosting is a similar technique to adaptive boosting, but it combines, again, a weak classifier or regressor into a strong method via a series of iterations. And in order to understand this method, what I want to do now is actually to take a look at a regression problem. It's often easier to look at things from a regression point of view than to actually do it in terms of a classification problem. And that hopefully exposes the basic ideas to you of these methods here. So we would typically, again, start with our cost function, which now is a function of y and a function f, which is our weak learner. And then we have a sum here over all the different contributions, and I normally refer these to the loss function. Some people call the cost function for loss function, as we met before. And the standard one is actually to take the mean squared error. And here I just skipped the 1/n term, as you can see, or plain laziness. And the same thing is being repeated now. What we're going to do is actually to define a new function, which is our weak learner, a real function, and that defines our final function. So what I have is a final function is simply a sum over all these different functions, h of n, as we did previously. Now, the thing now is that if we take a steepest descent approach, this is an intermediate step towards the full gradient boosting. So in this case, just keep in mind, what we are going to do now is not to find an ideal functional representation, but we are going to let the function be represented at the different points we are looking at. So we are calculating the gradient of this function which we have here, this loss function, the individual contribution, and we take that as a derivative with respect to the function f of x, which enters here. And you know that this is pretty easy to take the derivative of that function, because that simply gives us minus, and then we have multiplied with 2, and then we have y of I minus f of x. So that would be the derivative of that expression. And then this is calculated at the previous value, fm minus 1, as you can see here. Can you see well in the back there? Okay, good eyes. Then what you would do then is actually with a new gradient, we update the function with the previous value. And in this particular case, I'm going to have a parameter in front of it. So you could think of this as a kind of learning rate. Except that now, this is a parameter which we're going to optimize. So we have the gradient, which we calculate. And this gradient is now given by this function, calculated at the value x of I with f of x of I equal to the previous function. And if we look at the above, this kind of squared arrow function, you see that the gradient is simply given by minus 2 y of I minus f x of I. And if you choose f of 0x, the first iteration simply says that this gradient is given by minus 2 times y of I. That will be the first gradient. And then you can go back, and then you keep iterating. But before you do that, you insert this function into the minimization problem for the cost function. So that means that every step you have a minimization. But the minimization now is a minimization problem in terms of what you might call the learning rate, or a kind of pseudo-learning rate, or in this case just a parameter. But it's a kind of learning rate-like quantity. So what we are doing now is actually to update this function here with a gradient, where the gradient is calculated for every single point. The advanced method beyond this steepest descent, as it's normally called, is a method which becomes the gradient boosting, which we're going to see in the next step. So in this particular case, what we do now is that we take the cost function, we plug this one back again. So we would have it in here, plug it back, and then we optimize. And when you optimize, this is more or less as we've done before. When you optimize, then you could reuse your gradient descent method from project number 2. And then you find the optimal parameter. This is rho of 1. And when you have rho of 1, you move back, you redefine this function, and then you keep going. So that means that if you take a simple case where you can take the derivative, so if you now take this specific function here, you would have a rho 1 of g1 equal to this minus y of I. This is the following up this simple example which we see here, where we simply decided that g of m is equal to minus 2 times y of I. If you do that, in the next iteration, you will find that this is equal to minus 4 times y of I. And you would find a new value when you plug that one back again, where rho 2 is minus a half. And then you continue till you have reached m is equal to the uppercase M. And you can modify the steepest descent method, however, by introducing what is called gradient boosting. And let me just say a little bit about why we do that and then go back to the whiteboard. So the steepest descent is less used since it only optimizes f at a fixed set of points. And we do not learn a function that we can generalize. However, you can modify the algorithm by fitting a weak learner to approximate the negative gradient signal. And let's now try to see what that actually means by switching back to the whiteboard. But before we do that, I just wanted to show you some results, okay? Before we just spell out the algorithm. So if you look at the application of the algorithm, I'm gonna implement this one to a classification example, and surprise, surprise, the classification case is again the breast cancer data. And in this specific case, what we're going to use now is the gradient boosting classifier. And we are going to have a classifier of depth 3, and we are going to perform 100 estimations. So the loop M goes up to 100. And in this case, I put a learning rate to 1. So let's see what that gives us. And I'm going to plot the same quantities. I'm going to do the confusion matrix. I'm going to do the ROC curve and the cumulative gain. So if I run this case here, you would then see that I get a result for true positive, which is 94%, and 99% for true negative. And the test accuracy with gradient boosting and scale data is 97% when I take the average of these. But I could go back now and change my learning rate because I'm actually calculating gradients here. So we could now switch that one to 0.01, and let's see what happens then. And this case actually get 96%. So it's not given that by changing the learning rates to smaller ones gives you a better result. So these are things which you have to play around with. So let's try another learning rate here and see if we can improve it. And in this particular case, we actually back to 97%. I could make the tree a little bit more shallow. So I have an even weaker learner. So let's see what that gives. And that seems to give us a classification error, which is at the level of 98%. So again, when you run this type of calculations, you actually need to, as we said before, to play around with the depth of the weak learner, which in our case is a tree, and then also with the learning rate, which enters the calculations of the gradients and the optimization part. So here, when it comes to the gradient boosting, it's actually you doing an optimization problem. So not calculating the gradient, but calculating the gradient of the optimization problem. So let's take a closer look at what this actually means. And now we're going to switch back to the whiteboard. And perhaps we can take a final look here at what's normally called gradient boosting before we start looking at the details. So XGBoost is extreme gradient boosting. It's not a method. It's actually a highly fine-tuned library, highly efficiently made for high-performance computing, and it implements gradient boosting. And if you wish to look it up, there's actually an article by Chen and Westrin here. And what they design and build is a highly scalable tree boosting system. It says it has theoretically justified weighted quantile sketch for efficient proposal calculations, whatever that means. I haven't been able to understand that fully. But it's actually one of the algorithms which wins many of these machine learning competitions. One of the things you will see, it doesn't that well on regression cases. But if I now run this case here with XGBoost, you will need to install it as a library. So it's not included in scikit-learn. But you would actually have to install it as a library. So you could do a pip install or conda install. And then you would install ADABoost as a library, and then you can run it with all the functionality of scikit-learn. That's one of the nice things with many of these libraries. They interface perfectly well with scikit-learn. So what you would do then is actually, when you have imported thing, you run the calculations, and then you can see now that in this specific case, when I use ADABoost, I have a perfect fit here with 100-100. So this is actually the method which has been really fine-tuned to many classification cases. And you will see in the literature that's the kind of method which tends to win many of these machine learning competitions here. Okay, so if you try to run the regression case, you will be a little bit disappointed. It's not the same quality. And in this case, what I've actually been doing is to look at the squared error as the type of error which I calculate. And then I look at the polynomial degree here is actually the depth of the tree, where I run from a tree level of 1 to a tree level of 6. I invite you just to take a look and run these codes. But for classification problems, these methods actually do very well. So any questions so far? Okay, so I'm going to need a little bit more time to set up the final algorithm for gradient boosting and steepest descent. So I would propose that we stop here now, and then tomorrow we summarize trees and we look at the final algorithm for gradient boosting and steepest descent, which is also another variant of gradient methods. And then tomorrow we are going to start looking at support vector machines as well. So I expected actually to run a little bit slower, but I covered these topics a little bit more faster than I thought. So I will start tomorrow in the next section with our last supervised learning method, which are support vector machines. And these are methods which we will also spend time on next week. And next week, my hope is that we can also discuss or eventually have a workshop where we can discuss different types of projects, so variants of project number 3. Okay, so tomorrow we wrap up trees and ensemble methods and boosting, and then we move over to the support vector machines as our last method. And finally, the first encounter with unsupervised methods is going to be principal component analysis and clustering. These are the only unsupervised methods we will cover here. Okay, so I'm going to stop today, and we see each other again tomorrow, and best wishes to